All right, hello, sound, almost there, nope. Okay, there we go. My voice appears. Hi everybody. Good to meet you. It's been a while. You ready? Almost ready. Okay, hi everybody. So I'm Josh Hug. I am somewhat too loud. Let me try and adjust this. Okay, there we go. So I'm visiting from UC Berkeley for the semester. I'm on sabbatical. I'm doing some stuff here, a little bit with this class, a little bit elsewhere in the department, also for a friend's company. And so one of the weird perks of being a professor is every 10 years you can just go somewhere, and I've come here. So today, since Yao Chun's out of town, I'm going to be covering our class, and I figured I'd do a bit of a review. And I feel like this mic is still sort of horrible sounding, so let me see if I can adjust it. One moment, sorry. Okay. The one thing I didn't check. All right, volume controls. Okay, here we go. On volume. There's gotta be a way. Okay, I guess I just have to talk quieter. Okay. It will be fun, I promise, once I stop fiddling with my audio. I'm going to live with it and just try not to talk as loudly. Okay, so what I'm going to do is I'm going to talk about 3 big ideas from the class, and it's going to be a little bit of a bridge to other classes that you have taken or will take. The 3 topics, first we're going to talk a little bit about functions again and weird things that you can do with them. Second will be object-oriented programming, and the third will be recursion, and we'll do some cool stuff along the way. So the first thing I have for you is a little puzzle, and I'm just going to do a few of these. Well, let's suppose I define a function called chert, which is a type of rock. I don't know why I picked that name, but it did. And then I say a equals chert, b equals a, c equals b. What do you suppose will happen when I run this code? And if you're willing to entertain it, I'd love it if you'd go to this website link, yelkey.com/bed. This is a randomly generated URL that will have you fill out a Google form. So I'll give you guys a minute to do that. And I'm going to try and give you a lot of stuff to do today, because 2-hour lectures is 1 hour too many. So you need things to do. Otherwise, you'll lose your mind and become bored. Or at least I would. So I'm going to give you a minute, and I'm going to see if anyone's answering. Got a few responses. Okay, still gonna let it go, okay? Well, I messed up the poll, didn't I? It looks like the answers I gave, none of them work. Whoops, that's a bad look when you first get started with a lecture, isn't it? Okay, let's see what happens in the visualizer. Okay. Oh, right, that's why. Okay, want to try again? Okay, sorry about that. Okay, now try again. Let me change it so that you can answer again. I can see why you were panicking. Okay, responses. All right, give it another go. There we go, okay. I was worried, I was like, why is everyone getting it wrong? Because I got it wrong. Okay. All right, so let's walk through what happens with this example. Actually, I like these kind of problems where the real answer is not there, because it knocks the legs out from under you and you get nervous, and it makes you think, do I really know what I'm doing? Okay, so hopefully I gave some fear to you. So let's talk about what actually happens here when you run this code. Okay, so here's the same function we had before where I fixed this number to be 5. When I call def chert, this is a statement in Java, in Python. I usually teach Java. And what it does is it creates a new function called chert, and I'll note that that function is not called a or b or c. When I say a equals chert, I'm binding, that's the term I use at Berkeley, that function to the variable a. Then I say the function up here is bound to the variable b, then c binds to the same function, and then lastly we call it with the argument 1. So hopefully that feels comfortable. An alternate way of looking at this is to pop it in that Python visualizer. Oops, that's not ready yet. Okay, let's go to Python visualizer. Okay. So if I run this code, oops, I gotta take out some indentation. Okay, if I run this code, just to give you a different picture of what I mean by all that binding nonsense. When I say def chert, I have defined a thing that now exists in my space called chert. It is a function. When I say a equals chert, a points at that same thing. B points at it, c points at it, and lastly, we can print out the result of adding 1 to 5. Okay, any questions about that, or anything you want to tweak, or anything weird you want to ask? Okay, let's do another one that will be more interesting, and hopefully won't have a typo. Okay, all right. So, question, when I run this code, it's a little more involved, so let me talk you through it a little bit. We have a function up top called cube. It's simple, it takes an integer and returns the cube of that integer. And then I have a function called summation that takes 2 arguments, in and term. Okay. What it does is it iterates from k equals 1 to n, and as it goes it adds term of k to total. Okay. What do you think will happen there? So I've got another yellow key for you. Lecture is not just these type of questions. I just wanted to open with a couple. And I'll double check my answers are right this time. Okay. And I'll double check that my link works. Okay, good. Okay, I have 1 response so far, so I'm gonna wait till I get around, I don't know, 15. Okay. The answers are doing pretty well. The not answers, I don't know what's in your heads. Okay. So let's talk about this code and how it works and what answer we get. So you might have sensed roughly what it's supposed to do without being able to follow it closely, but the basic idea is what it's going to do is it is going to go through all the k's from 1 to 3. I shouldn't show 0 here, sorry. So it's going to give me, the first time through this loop, it's going to say the total is equal to the total plus term of k. But what is term? What is term? So this is a variable. What is it? What's in it? What's it bound to? Cube, the cube function, right? And why? Well, because when we called summation down here, we passed in cube as term. So what it's going to do is it's going to add to the total 1 cubed. Then it's going to add 2 cubed, then 3 cubed. And so that's 1 plus 8 plus 27, which is 36. And so as before, we can look at this in a detailed way, and then I'll have a question for you. Again, not a Yolki question, but a question. So we'll note here, we have a function called cube, and I'll note that that function is not called term. It's called cube. Then here, in the summation function, we have a variable term, and that's some parameter. The term that is used in the intro class at Berkeley is a formal parameter. It doesn't really matter. Just using the terminology today. And that's something that will later be bound to a function. Right now we don't know what it is when we're writing the summation function, but it's something that's expected to be a function. Then down here, I will say this function, whatever gets bound to term is going to get called on this line. And then on this very last line, whenever you call print summation 3 comma cube, the cube function is passed as an argument value. Thus, this term variable gets bound to that function. Did you know you could do that? I don't know. Who knew you could pass functions as variables and felt like, okay, cool. Who did not know you could pass functions as variables? Okay. So, Python is a language which is extremely flexible and lets you do all sorts of weird stuff. And this is something that is actually genuinely useful in some cases. I mean, this is an example of when it's useful, but we'll see a more practical example in a moment. The way of thinking about this is that in programming, one of the things that you'll pick up, especially when you take the data structures class next term or next semester, is that we want to build code that captures abstractions, pieces of functionality that can be reused, and sometimes those pieces of functionality can be a little bit meta, is the term I would use. This idea that I want to be able to sum any series. And what do I need to be able to sum any series? I need a function which gives me the next term in that series. Okay, so this is an example of a function which takes a function as an input. In principle, that's something you've seen before, but it's something that we haven't really gotten a lot of practice with in this class, but you will later and a little bit today. Now, as I just said, one of the main reasons that we write code is to capture abstractions we can use again and again. So when we write a function, we're trying to capture something. We don't want to repeat ourselves. We want to have one piece of code that can do anything that is useful to us in some specific domain. And actually, one of the hardest challenges whenever you write big programs is figuring out what are the things I need to abstract? What are the functions I need? I'll give you an example at the very end of the lecture today that's quite tricky. So the function that we're writing, it's some common structure that we can use over and over. Okay? So for example, we could use that summation function, that thing that I gave you as a puzzle, to sum any type of sequence. The only thing we need is a term function that will give me the next term in the sequence. So for example, if I want to sum the first so many natural numbers, then I just need a function that returns the natural number. So term would just be return x. This is the one that we did in our puzzle, return the cube. But we could sum other stranger series, like this series, by just defining a function that returns 8 over 4k minus 3 times 4k minus 1, and we could use that to compute this value. And we could use that same summation function over and over, we just have to write a different term function. Now again, that might not seem so practical. Like, how often do you need to sum series in your daily life? Not necessarily super often. Okay, so let me give you another example, and I'll be happy to take some questions after. Okay. Oh, by the way, these are just the terms. All right. So here's another example, which is sorting. Okay. So let's suppose I have these numbers: 4, 4, 4, 4, 1, 2, 3, 4, 5, 6, 7, 8, and so forth. Just a bunch of integers. And by the way, you'll notice these integers have a nice structure. Anybody want to guess how I picked these specific integers? I'll give you a hint. When I had my browser open, there's a ChatGPT window. So I said to ChatGPT, I want a set of 30 integers that are less than 5 digits that are kind of interesting. These are the ones it gave me. It's so good. Isn't that great? Saved me like 5 minutes. Anyway, so if I call sorted on this list, what I will get back is a sorted list of integers. Okay? So let me go into this code here. Sorted. I don't know, I double printed. Okay, here we go. So here's all those integers that ChatGPT gave me. If I run this code, they are in sorted order. Okay. Now this seems like a little bit of a disconnect. I was just talking about generalizations of functions that can sort anything in the, generalizations, something that we can reuse over and over. Functions that take functions. This seems unrelated to that. Well, I will bring it together by saying, what if I don't want to sort the numbers in order? What if I want to sort by some other property of the numbers, rather than which one's bigger? So I don't know, someone give me a way to sort numbers that's different than which one's bigger. What's that? Number of digits? Okay, that sounds good. And I'll do another one, sure. So I'll start with number of digits. So if I do def num digits, I'm going to write a function that tells me how many digits are in a number. Here's x. And how do I know how many digits are in a number? Anybody want to suggest the laziest possible way to do this? What? Yeah, you could do like a for loop where you like say, let's do some like blah, 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 x divided by 10, some counter. That's the easier way. That one's fine, but this is a stupider and better way. Yeah?
You're going to turn it into a string and
yes. Turn it into a string and get its length. That's my favorite way. Is that way better? It feels kind of dirty. Like you've taken a number thing and you've turned it into a string thing, but I think it's fine, right? Is one of them faster than the other? Probably this one. I don't actually know. I don't know. Actually, maybe it's the other way. But you know, we don't care. This is such a small little function. I don't care if it's slow. I just want it to be right. So I'm going to return the length of the string of x. Now I'm going to do a quick test just to make sure it works. You know, to feel comfortable. Okay, so how many digits does this number have? It should be 5. I can't imagine that it's wrong, but that way we feel good. Okay, hey, it's 5. Good. All right. So now what I'm going to do is I want to sort L by the number of digits. Well, it turns out that the sorted function takes another argument, which is called key. And you give it a function, and it will sort by that function. Okay? So this is something very practically useful. I use this all the time. If I do this, now they're sorted in order of number of digits. You'll notice that that's also closely related to the size of the numbers, but there's no particular ordering between the 3 digits numbers within each other, right? So we get some bigger ones before the smaller ones. Give me another way. Go ahead. Yeah.
Is there like a option to
Switch the order, yeah. So you could, I think it might be called, I don't know, honestly, I've kind of forgotten. Ascending, is that a thing? I've used Python, that's not a thing. I don't know, let's see. Ascending equals false. Let's find out. That's what I would do in another language. No, okay, ascending is not a thing. Anybody know off the top of their head? I mean, I could do, for example, negative here. That would be one way to do it. I can also do reversed. That's probably the most Pythonic way of doing it. If I do that, it's probably fine. Whether or not there's a way to tell sorted to go in reverse order, I actually don't remember. Oh, then it's an iterator. Okay, so now I turn it back into a list. Okay. So this is where, of course, I would recommend that if you're doing a real-life programming project, this is when you turn to Google and you say, is there a way to sort in reverse order? And someone will give you the nicest answer. But this isn't something that I know how to do off the top of my head. Okay. What I don't recommend necessarily is, until you get to be better at programming, I don't know that this is a good time to turn to ChatGPT because it's too small, right? It's better to get the search skill down. But I think ChatGPT, by the way, is a really, really good way for learning how to program, especially when you have something slightly more complicated. I'm taking a Dutch class on Tuesdays, and I use ChatGPT all the time, but only because I have like complicated questions that I can't necessarily get answered. And you too should probably avoid ChatGPT for the small things. Okay, anyway. So we'll go away from that. Other questions about this before we do another example of this? Okay, give me another way to sort numbers that's different. Just to, I don't know, because we can. Yeah. Sum of the digits. Okay, sum of digits. That's a good one. Okay, how do I do that? Let's see. That's when I might do the loop thing. Yeah. Sure. How do I want to do the digits? I don't know. Do I really want to divide by 10 and everything? Maybe. I'm going to try it. Okay. I'm going to do it. Okay, how about this? I'm not going to get ahead of myself. I was going to maybe do it recursively, but I'm not going to. Okay, so I'm going to do some, that's a special word, I think, maybe. Total equals 0. Then we'll do bottom digit equals x mod 10. Total equals total plus bottom digit. And I need to repeat this like so. I think this works. I don't feel 100%, but I'm pretty close to 100%. That's one way you might write it. There's many other ways to do it. Let's test it. Sum of digits. I mean, I would not be shocked if this was broken. So if this works properly, I should get back 13. Okay? None. Oh, I forgot to return. Okay. Let's make this bigger too. All right. So we get 14.4444. Okay, well that's not good. I got to do like that, right? Yes. All right. That's the integer divide. 13. Okay. Do you know what this is? Double divide? Feel good about double divide? Don't feel good about double divide? Okay, let's talk about that for a moment. Just a little journey. So if I do 14 divided by 10, I will get 1.4. Okay. If I do 14 double divided by 10, then it is divided by and then rounded down. You truncate the rest off. Or I do like 274 divided by 10 is going to chop off the bottom digit. Okay. I don't expect that you feel comfortable with this, but I do, and so that's how I wrote it. But you might have written it a totally different way. I'm happy to go in any direction today, too, by the way. Go ahead.
Is it the same as writing div in C++?
Div in C++. I don't remember div in C++ because I haven't written C++ code in a long time. Let's see. I don't know. Let's Google it and not ChatGPT it. C++, div. Okay, the standard library. The integral quotient. Do I trust programiz.com? Sure, okay. Integral quotient and remainder. It returns two things. Oh, it's a structure. Sounds like, yes, it's part of it. Sounds like it's the quote part of div. Anyway, nobody here is expected to know any C++ today or ever. I'm guessing. At least not in the study program that you're doing. I used to write, one of the first programming languages I learned was C++, but I haven't touched it in a long time. Other questions? Okay, so this is a powerful thing to be able to do, to say, oh, we didn't actually do the sorting. Let's sort by the sum of the digits. So here we go, 2001, that's the smallest one. Now digits only sum to 3, and it goes up to 9999. Now I just claim that I do this sort of thing all the time. It's not clear why you want to sum numbers by some other property, but certainly there's times when you want to sort data by various properties. So for example, let's suppose you have a data frame, which is a data structure used for storing tabular data that you will certainly use in this study program. And you want to be able to sort, say you have a big table of information about countries. You might want to sort by their GDP, or you might want to sort by their life expectancy, or you might want to sort by their GDP divided by their life expectancy, something like that. And these type of things are extremely useful, and this is exactly the kind of code that lives under the hood. Now, often, you're not going to be using sorted, but you might do something. I think it's called sort values in the library that you'll probably use when you're doing data frames, and then you pass a function about how you want to sort them. So this is very, very normal and a very lovely place where passing functions as an argument is really useful. Okay. All right. Any other questions about this? Okay. So where does sorting come from? I'm just going to talk about that for a minute. This is a tiny preview of the sort of thing you'll see in the data structures class. I want to write sorted to get a sense of, okay, well, how would you actually do this? Like Python has the ability to do this like magic, but nothing in programming is magic. Some of it feels nearly magical, but this is a function we could write, no problem. Okay. So I'm going to write a function called Josh sorted, actually. I changed my mind about the name. So Josh sorted, since I am Josh Hug is my whole name, I'm going to write sorted. Okay. So how is this going to work? Well, there's a lot of different ways that you can sort. If you take an algorithms class someday, you'll see there's like a half dozen really important ways. And in fact, on assignment 4, you'll see a sort called merge sort. I'm going to do a sort that is called selection sort, but this is a piece of lore, it doesn't really matter. And the key abstraction for my sort is I'm going to have a function that has a very specific and kind of quirky behavior. It's going to find the smallest value in L, and it's going to return it. Okay? Then it's also going to have a side effect. What is a side effect? Anybody remember? So if you have a function, what is a side effect? Yeah.
It's just like what happens in general besides returning certain values.
Yeah, something that is observable other than the return value. So what's an example of a side effect? Well, there's this one, removing the thing out of the list. The list actually gets modified by this function. What's another example of a side effect? Anybody got one? I'll give you one. Printing. If you print out output during a function, like you might have been debugging a function in this class at some point and added a print statement to help you debug, that's a side effect. Anybody want to throw out another idea of a side effect? Anything at all. So you run a function on a computer. Something happens that's not a return value. Name something your computer can do that's not returning a value. I believe in you. Well, this is getting awkward. Oh, did I lose you? What's that? If you modify some variable, it's a global variable, sure. There's other kind of side effects too, like beeping, sending some packet over the internet, displaying something on your screen. So side effects are pretty important. This one, though, this side effect is very data-y. It's just going to affect the list that's been passed in. Okay. So why am I using this function? Well, because I decided it would be good for lecturing. But it's the choice about what abstractions you're going to support that's really important, and it makes all the difference in how well your program runs, how hard it is to write. That's something you'll come to discover later. And what I mean by that is, I could have written something else entirely, like just find smallest, and maybe find smallest just returns the smallest item. Okay. To you, there should be no obvious reason why this is better than this, but for me, it's going to be a little easier to talk about during lecture. Okay. All right. So let's start by writing extract smallest, and then we'll write Josh sorted in terms of extract smallest. So I want to find the smallest item in L, and I want to return it. Well, how do I do that? One way I could do it, well, I could do something like for x in L, smallest item equals, I don't know, let's say L0. For x in L, if x is less than smallest item, then what? Yeah? Yeah, take the value of x, and then we could return x. Okay, great. So that's one way I could write this. There are other ways to write it, but there's one thing I haven't done, which is to delete the smallest item as a side effect. I guess I feel, well, actually, how could we do this? I'm going to stick with this structure. It's different than the one I did before class, but there's one thing I haven't done, which is removing the smallest item. Anybody know how to do it? Right, so we got that part, but the part is that L still has the smallest item. So how do we kick it out of the list? Yeah. Here we could pop it. Okay, so whenever we're done, we could do like L dot, we could try doing pop X, though I don't know that this behaves well, because if we highlight this, we see it's yelling at us and it's saying, smallest item. Okay, so again, not being someone who writes Python all the time, I feel a little nervous about this. Like, I'm not sure that pop actually removes by item. So I'm going to go to the Python reference manual, or wherever. Python pop method list. Okay, here we go. No, it's program is again. Why does program is get all my attention today? Okay, here we go. Let's do pop. All right, I feel better about using the python.org docs. Dot pop. Removes the item at the given position in the list. Okay. So that's not quite what I want. So popping, I could do it, but I need to get an index. What's another thing I could do? Remove. Okay, which one do you want to do? Who wants to do remove versus who wants to do pop? Okay, remove. Okay, who wants to do pop? Okay, removes win. All right, so let's try it. Okay, L dot remove smallest item. I think that looks fine. Okay, so that should be good. And then return, not X, return smallest item. Boy, okay. Okay, so now let's test it out. And let's do that by, I'm going to make a smaller list that's easier to look at. All of L equals 5, 2, through 1, through, that's not the numbers I wrote. Okay. So when I do L extract smallest L, So what I expect to be printed first, actually I'll do an S string, how about that? Or F string. The smallest was S, and after the list is L. Okay. So let's run it and see if it worked. Probably it did. All right, the smallest was 1, and afterwards the 1 is gone. Okay, that looks good. I feel pretty good about the function. In real life, we'd write some kind of more sophisticated unit test, but we haven't really talked about that in our class, and that's okay. Print statement will do it for me. Now, one thing is when I write code, I do this all the time. And I advise you whenever you're writing code for assignment 3 or 4 or anything in the future classes, is that you want to be building confidence in the basic building blocks before you try and use them. Because otherwise the problem could be anywhere. Okay, but here I feel pretty good. I'm going to note something about the way I wrote my little test case too. You'll notice I put the smallest in the middle. Anybody want to guess why I did that versus like putting it at the front or the back? Yeah, I want to give it a more probable case or less of a corner case. Because if you had a bug in this code, I wouldn't be too surprised if the bug was it always returns the first value, or it always returns the last value. And this is just something that comes with practice. I give it an input that seems a little more challenging and generic. Now this doesn't prove that it works, but I feel pretty good that it does. Okay. Is there anything anybody doesn't like about this function? I mean, it works, but anything people don't like about it? Ooh, the smallest item doesn't exist. That's interesting. Okay, so there's a few things that could happen. Like if the only way there could be no smallest items is if there's no items, though. There will always be at least something. But if you have an empty list, it could fail. Okay, fair. So I could fix that, but I'm not going to. Another one I'll throw out there is that it's not exactly efficient because the way the remove method works is it's not really a nice way of doing it. Like, just this idea of this function to me feels weird. Like, removing things from the middle of the list, as someone who teaches data structures, just feels dirty. Like, you shouldn't be doing it, just like the wrong way to use a list. But that will come in time. Okay. For now, we're just going to accept it. All right. Okay, so, and the reason is that when you remove something in the middle of a list, under the hood, secretly Java has to move everything over, which can be slow, but it's okay. We don't care. By the way, I hope that my little digressions like that are enlightening and not scary. I just throw in things out there that I happen to know. All right. So next we need sorted. Okay, so what we're going to do is we want to use extract smallest to get the list into sorted order. Okay, so I'm not going to return L. I want to do something else. Anybody want to guess how we might start the process of sorting? What's that? What kind of sorting? We're going to use extract smallest. So it's going to use, this shouldn't say the key function. That doesn't exist yet. Sorts the given list. That's coming soon. Okay. The sorting technique will be based on extract smallest. Okay, so that's the basic tool you have. It's the only thing you have is the ability to extract smallest. That's the only ordering based thing you got. Well, let's do kind of a lazy thing and say, I don't know, smallest item. Smallest equals extract smallest L, okay? Now what? We have the smallest thing. We don't want to return smallest, right? Because that's only one of the values. We want to do something better than just that. Yeah? Yeah. Call it sorted list. Sounds good. And we'll do smallest equals extract smallest, and then sorted list append smallest. Okay, that's a good start. That'll create a list with the smallest item up front. Okay, someone else want to suggest what we need to do to change this? Yeah? Right. So we just need a loop. So we need a loop, I agree, while something. Do this. We could use a for. I think while actually feels better to me, though. So how long are we going to do this? We have our list. We take the smallest thing out and put it here.
So while the list is not empty.
Yes, right. So while while L, length of L is greater than 0, something like that. You could also do while L. That's just a little trick. So as long as the list has something that's equivalent to while length L is greater than 0. So I'll do while L. And then when we're done, we will do sorted list. Okay, so let's try it out. And so we just created our own sort. Okay, so sorting is not magic, and here we did it. We sorted. Okay, great. Okay, any questions about this? Okay, back to key functions then. Let's do it. So now I want to sort by the given key function. So now I want to be able to sort. I'm going to take one of those functions we had from our other example. Let's use this one. Thank you for the suggestion. Okay, we'll bring this in over here. And yes, there are ways to like import it from the other file, but we're not doing that in this class. So I want to do sum of digits. So if I do this, sum of digits, nothing different will happen because we're not using sum of digits. Technically, the Josh sorted routine receives sum of digits, but it is not using it in any way. So how do we use it? What do you think we should do next? Yeah. Right. We need to extract smallest to also be able to think about a key function. Okay. Uses the key function to decide smallest. Okay. And now they think maybe the it feels sort of magic that this works, but okay. So how do we use the key function? So remember, if you're having a hard time thinking about how to do this, think of key as it is sum of digits. And we have a specific thing to think through. Okay. So if this was sum of digits, you can just fill it in your mind. How do you do it? Yeah? Right, exactly. Okay, so if you got stuck thinking about how to do key, well, just pick a function. And then you're like, well, I don't want it to always be sum of digits. I'll call it key. That's a better name. So I just take the key function, apply it to x, and check if it's smaller than the key function applied to smallest item. And that's it. And once we do that, we are sorting by, almost. I forgot to do something. I forgot to actually pass the key function to extract smallest. Okay, so we did it, and we get the number sorted by a sorted order. Okay, so we built our own sorted function. It takes as input a function, and it lets us do this, and that's great. Okay, I think that's really all I have to say about functions for the most part, but let me see if that's true. Maybe I had one more. I have a little more. Okay. Okay. I had more. Okay, that's the function I wrote, but this version is easier to see. Any questions about this? Or things that you're inspired to ask or change? Yeah. What if the key references itself? Well, that's super interesting. So if the key function were recursive somehow, can I make that happen here somehow? Sum of digits. Sure. Actually, I can do that. I don't know if this is exactly what you're asking, but okay, let's do it. Sum of digits. We want to return x divided by 10 plus sum of digits x divided by 10. I think that this sum of digits function works. We'll get to recursion again later today. So we take it, we get its bottom digit, we do sum. I forgot one thing though. If x is less than or equal to, well, if it's just 0, return 0. Okay. Don't expect you to feel comfortable with that. But here we go. Sum of digits, 3, 1, 9. Okay, that's going to give me 13 again, hopefully. Did we do it? We got it, okay. So this is a key function that references itself. So when you run this code, the key function, when it gets called, it calls itself over and over until it gets to this base case. I don't think that's what you meant to ask, but that's literally what you asked. If this strikes fear in your heart, though, this other loop version's fine. I'll give us some recursion practice in a little while. Okay. So, next question, and this one you don't have any way to answer it on the compute or on the yell key. Let's suppose I have this code right here called PowMaker. Okay. PowMaker, very vexing function. Inside of it, it says def. Yes, def inside def. So even if you're not comfortable with the syntax, how do you think I would use PowMaker to compute the square of 5? So I guess what I would ask first is, what type of thing does PowMaker return? Yeah? Some. Well, I heard a voice closer. I haven't heard. Yeah, go ahead. Return one more time. Yeah, a callable object, a function, right? So this function returns a function as an input. And so if I wanted to use PowMaker to compute the square of 5, what do you think I do here? As a first step. So I want a callable object, a function that gives me squares. So what do I put here? So I just need one thing in this parentheses. I'll give you a hint real quick. So I'm going to have a function here called, so square is going to be PowMaker, and then I'm going to say print the square of 5. What do you think goes here? 2, right. What's going on here? Well, what's going on is the PowMaker function takes as input 2. It then declares a function, which is x to the 2, and then we return that function. Okay. Now, if I run this code, I do indeed get back the square of 5, which is 25. Okay. Do I? Really? Okay. x5 puzzle 3. Yeah, okay, great. Okay. I will have a visualization here that will make you feel more comfortable. All right. Let's see. Yeah, okay. I'm not going to take questions quite yet. Okay. So this is an example of a function which returns a function as an output. And so this example is a little silly, but when you get to classes where you need to optimize functions, so there are cases in data science and machine learning in particular where I see this all the time, where I have functions that return functions. And I'm going to say words at you, but they may not make sense. So let's say you're building a model that's supposed to predict house prices. This model takes as input a bunch of parameters for the model and data about the market, and then it produces an output that says these are what I predict the house prices will be. The way that this technique is used in ML a lot is you write a function that takes your data and that big function of both parameters and data and makes it into a function of only parameters, and then you optimize. Now, I feel bad even just saying those words, but maybe maybe 3 people in here got it, and you're like, okay, cool, I see. But everybody else, sorry. Okay. We're just going to stick, though, in this class, just the idea of this. So you just have to trust me that it is useful at some point in the future. Let's talk about how it works. Okay. So to drive home, and one of the big themes of today is to really, I hope, demystify programming, that it's not magic, that sorting is not magic, that passing functions as objects is not magic. Here's another thing that we can do that might feel awkward at first, but when you get this, you have a warm feeling in your heart. You're like, yes, I'm really understanding what's going on with programming. So I'm going to note that I don't actually need to assign the result of PowMaker to square. I could actually call the function directly without ever giving it a name. So I could say PowMaker2 5, right? So this right here, PowMaker of 2, that is square, and then I give 5 to that. Okay, so that's, when I say why does it work, that's why. Let me give you a picture in a sec. Okay, so let's go back into our code though. I'm going to show you real quick that really I can just do this. Print PowMaker 2 square, or sorry, PowMaker 2 5. So when I run this code, it really just works. I get 25. Okay. And the reason is that this right here, what is that? The thing that I'm highlighting, that might be kind of hard to see. It's not so bad. It's the result, it's the square function. So if you don't like that, here's one more visualization that might make you feel better, which is the following. You may remember, like, I don't know, a lot of weeks ago, lecture 2, I talked about one way to think about function expression evaluation. So when I say PowMaker2 parentheses 5, that's the piece of code I have here with extra spaces for some reason. So this right here, this is the operator. Over here is the operand, and I know you haven't seen those terms in our class since my guest lecture before. And this right here, unlike most situations, this left side is going to be an expression that evaluates to a function. Okay, so PowMaker2 is an expression here that becomes a function. And then this right here, this is going to be an expression that evaluates to the argument of that function. So 5, of course, is going to be very simple to evaluate. It's just 5. But I could have like 5 plus 2 in here or something. Okay, so what happens? So PowMaker2, well, when I look at this, again, I have a situation where I need to evaluate the operand 2 and feed it to the operator, PowMaker. And so what is PowMaker? Well, this function right here, PowMaker, is the left-hand side, is the operator, 2 is the operand. And when I feed 2 into that function, what does it do? Well, PowMaker does this. It defines a function f, which returns x squared, and then it returns f. Okay? And so the return value is a function, and so that's what gets passed up into this little box. So remember these little boxes up top in my guest lectures are the result of the function call. Okay, so now that we have this function, we can now apply the 5. And so this whole thing, if I take 5 and put it in PowMaker2, which is the function which squares, I get 25. Is this maybe a little, a lot of machinery, a lot of visuals for maybe a concept that's relatively, I don't know, kind of straightforward? Yes, but I still find it personally helpful. Yeah. Yeah. Mm-hmm. So if I had 2 functions, give me a little more. I don't think I quite. Mm-hmm. Oh, if I had two variables or something, like a 2-variable function? Or two different functions or 2 different parameters? Mm-hmm. Right. Like maybe we'd do PowMaker 4 or something like that? Mm-hmm. Ah, right, okay. So maybe I would return like x, I don't know, plus n or something, right? That? And then I return fg. Yeah, so if you could, and so what this would do is it would return a tuple of functions that you would then need to unpack on the other way out. I don't know what this code will do. I don't think it will be happy. Yeah, because it's going to try and pass 5 to a tuple. I'm going to do this. I'm going to undo it in a second, but this would be like fg equals PowMaker, and then I could do f of 5, g of 5. That would be okay. Does it make sense? Yeah, okay. All right, I'm going to undo all that, and then I'll take the other question I saw waiting. Yeah. When is it better to do this right here? No. Oh. In general. Oh, I see. Right. Why not have, yes, right. When is it better to do that? Because the alternative, of course, is just to use the pow function. So I could do pow 5, 2, right? Pow is a 2-parameter function. Okay, question for you. Who likes this better? Nobody. Okay, right. So you're exactly right. You would never do this. This is just an illustrative example. And so one thing I haven't really done for you is justified that this is something you'd ever actually want to do. I have this vague notion that this is useful in the real world, but we don't have a good example. Yeah. 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 Oh, say G gets an argument, but F doesn't. Okay, yeah, sure. So let's do that. G return 33 plus F. I don't know, 3. Yeah, 33 just for some reason. Okay, so in that case, we would do FG equals PowMaker 2, and then we could do F of 5. But if we did G of 5, then it'll yell at me, and it will. It's smart enough to know. Yeah, unexpected argument. So, in short, it's whoever uses your two-function generating function needs to be aware of what it's supposed to do. Yeah. Let's see. Well, so these two are just generated in a totally independent manner. So, how would you like me to tweak my example? Okay, yeah. Yeah, so this just won't work. Yeah, if you run it, it'll say unexpected input for G. G takes 0 arguments, but you gave me 1. So this is a user error. The person who used PowMaker forgot they're not supposed to give it a parameter. I'm impressed that PyCharm can tell that it's not supposed to have a parameter. Cool. All right, any other questions on this one? Okay, that's probably a good time for a break, I'm guessing. Let's see, do I want to? Yeah, I think so. Okay. Yeah, okay, let's call it a break time. Okay, so we're gonna take a break for, I don't know, 7 minutes. And then I'll just keep going. I'll take questions in the meantime though. 7 minutes. Hi.
Nice setup of the lecture slides.
Yeah.
First about the summation, which can be used for AI
Yeah.
and vector analysis.
Yeah.
And then the functions inside of functions can be basically thought of as a class followed by object-oriented programming. Are you going to end it with combining everything
Yes.
with each other? For,
Yeah, the
like
plan
how
is-
to create and know?
Yeah, I'm gonna combine everything, not explicitly. I'm not gonna build an explicit thing, but we're gonna use recursion. I think at the very end, I'm not using functions inside functions, but I am gonna use object orientation and recursion together at the end.
To get an
Yeah, 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 yeah. Hi. Sure. Yeah. 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 Oh, something in your code is super slow. That's the problem you're having. I will try and spot something. Yeah. Right. Right. So it's slow for the bigrams or the trigrams or both? Or? Right. With bigrams, it's behaving very slowly. And how do you know? How do you know that it's slow beyond the level that is reasonable? Right. Yes. Yeah. Right. Right. And it didn't get very far. Yeah. I'll take a peek and see if I see any obvious.
So this is the bigram.
Yeah. I see. Okay. So it's a nested. Double. Right.
This is in percentages. So
I
it's
see.
only when
When it gets to 1, it would be done, or when it gets to 100? Okay, got it. Yeah. So, Having not done the assignment, the diagrams, so building, counting all the bigrams, is that what you're doing? The goal is to count all the bigrams in the text, again, because I haven't done the assignment.
So the goal for the Bible is to,
Yeah.
just
Yeah.
create a dictionary that looks for example every word and looks
Right.
at the probability
Right.
of the next word.
Right, okay, yeah.
The presentation of that
Yeah.
word.
Okay, so chiroptic. The only thing I'm worried about, but because I can't parse the code very well, but say it well, is that if you're doing a nested for loop, it's possible that something is like if you're going over all like if the way your code's structured is you look at the first word, then all the other words, then the second word, then all the other words, then the third word, then all the other words. Yeah.
What it does is first it creates the next word.
Right.
It creates a dictionary
Right.
that has like as the keys every word that the word twice.
Right, right.
It only has every word that it goes with.
Totally. Yeah, but my only worry is that somehow your code is accidentally doing that. Like it's iterating over the square of the number of words. Well, I don't think that a so what I would recommend is put away your comprehension for now, because having it as a comprehension versus an explicit loop is unlikely to make it very much faster. Right, okay. Yep. Ah, right, okay. So you started with the explicit loop and then went to the comprehension. Yeah, n's gonna be super slow, right?
It's first of all slow and second
Yeah.
it only gives the first occurrence, but
Right.
to upload it as a first it really doesn't read through every single word. What I do is if I go to a word and I read through the whole list of each word.
Right. I don't have a good way to help, unfortunately. I'm gonna take this one now, yeah. Yeah. What are you trying to do? You don't like that it's a bit magic? You don't want it to show the root or something? Right. So you're trying to print it out at some point? I mean, I think it's okay. It's just print out. You want to print out all the items. If you want to print out a dictionary more nicely, I think you have to iterate over it. I'm not really sure though. Yeah. Since I don't know the assignment well, I'm not sure what the thing is with it. It's weird. But I get Right. That's right. I would post on the forums because Yona's pretty on top of it. So I would say, what does it mean that you're like, oh, I think maybe that's just saying that's how many tests you passed so far. Yeah, you're passing all of them. Yeah. Haven't done the assignment. Okay, hello, hello. No sound. Okay. All right. Okay. Hi. Okay. So let's keep digging into, now we're talking about object-oriented programming. And so let's imagine that, to set the setting here, that we are trying to write code for some automated cash register where you pay with cash, and then it says they need 77 cents, and you're trying to save the checker time, or it's a automated machine totally, and so it's supposed to dispense coins. So the hardware has some function called dispense coins. Who knows how it works, but you have to give it some coins. So we have to decide on some kind of data structure for representing the coins that we want to give out. So I don't know, what might we do? A list, sure, a list of integers. So that seems like a perfectly reasonable possibility. And I think that's a great starting point. Okay, so you could just use a list of coins. I'm going to do something different, which is I'm going to create a class called coin combination. Why would I ever want to do that? Why not just use a list of coins? Yeah?
You might want to dispense, let's say, like 3 times 50 cents, 2 times 20, maybe.
Well, so you want to do 3 times 50, 2 times 20. You could have a list, though, that has 50, 50, 50, 20, 20, and that would be okay. Yeah? So what does a class get you? Like, what's better, potentially, about using a list versus a class? Sorry, a class versus a list. Yeah? Right. So you can make sure that certain combinations are, I don't know, valid or something, or like you can restrict it. You can give a little more logic. You can make that live as part of a class. So for example, so in the American market, there's a 25-cent coin, a quarter. Those don't exist in euro coins. And so you might want to have only some specific set of coins that are allowed. And one way to organize your code is to build a class. You don't have to do it, but a class is one way to do things. So object-oriented programming, it doesn't do anything new. There's nothing new that you can do with OOP that you can't do with normal non-object-oriented programming. But the basic idea is that you're going to take your data and you're going to abstract it, and you're going to, crucially, what I mean by this? What I mean is that rather than passing a list of integers around, I'm going to have an object called coin combination, and you don't know if it's a list or a set or whatever. It's a coin combination, is what it says it is. And that seems like a very subtle distinction. But another example that you'll see on assignment 4 is there's a person class. And you're not thinking about what's inside the person class, there's just a person. Another thing that's nice about OOP is that you're bundling together behavior and information. So you have your actual coin combination, that is what the coins are, but then you also have the code that mandates that you can't use certain illegal coins, right? You can't have a 25-cent coin in the euro market. And it's going to be part of the code that handles coins. It's actually going to have the rules built into that code, as opposed to some functions defined somewhere else. Now that might seem kind of wishy-washy, and it's a little vague, but once we see in this class, it'll make it a little more clear. It's also a way to think about, as noted here, distributed state. You have different coin combinations in different machines at different times, and every one of the objects, every coin combination has its own local state, and every object knows how to manage its own local state, like how to add coins or remove coins or whatever else, and it's going to use method calls to get the information that you want from the object or to modify it in some way. And then method calls, you can think of them as ways that objects can communicate, so to speak. All right, I don't know, it's kind of a little vague, but, oh, sorry. All right, and several objects, what's nice is that they can all be instances of a common type. They all have the exact same interface. They all have a value function. And as you saw in the inheritance lecture, different types could be related. Like you could have a wolf, which is a type of animal. We're not really going to talk about that much in this class, and it's a feature of programming that is, I'd say, less important than other things in this class. So there's a bunch of syntax out there to support these metaphors, like the idea of a method as opposed to a function. And so you'll see that occasionally in the context of object orientation, things have different names, like message passing and method and so forth. I'm not going to go into it so much here. Okay. So the idea is that you could have someone named John who has an account and someone who has an account who is named Jack. It may be that we want to withdraw $10 from John's account and deposit $10 in Jack's account. Okay. And so there's function calls that you can use to process this universe of things I'd like to do in the context of a larger programming system or a real-world system. But let's focus on, I was actually going to go straight to my goal, which is to build a coin combination. So the goal is this coin combination class is going to represent some combination of coins. It's only going to have one method called value, which is the value of the coins in the collection, in the combination. So for example, if you have two 20-cent coins, it will be 40. We want it to be iterable, meaning we can iterate over the collection. We want to be able to add coins to an existing coin combination. So if I say coin combination CC plus 5, you get a new combination that's the original plus 5 cents. And we want to have a nice string representation. The coin combination class I create is going to be immutable, meaning it can never change after it's created. And so let's just jump in and try this out. So here's coin combination. Here's some things we want to be able to do. Create a coin combination, add 20, add 20, add 5. Then when we print its value, it should be, what do you think? I believe in you. But I'm going to wait until I hear it. Maybe it's hard to see. Say again? Oh, the default is going to be no coins are present yet, so 0 value. Okay. So what happens here? Now we have 20. Now we have 20, comma 20. Now we have 20, comma 20, comma 5. Okay, so the value is, for those of you who are screaming inside but unwilling to speak, yeah, it's 45. You were right. Okay, when we print CC, we should get some nice picture of it. Okay, so I'm going to start by, one thing I didn't mention I want is, should prevent bad coins from being added. Okay, so to do that, I'm going to start with valid coins. I guess I'll call it valid coins. I'm going to use 50, 20, 10, 5, 2, 1. Okay, that's just going to be a class variable. And then what I'm going to do is I'm going to have, when we initialize one of these objects, it's going to initially, coins in me, I guess. It's going to be a list of nothing. You could use something else other than a list, but I'm going to use a list. If I want to do value of myself, okay, what do I want to do? Add all the values? The laziest way to do that, how do you add all the numbers in a list? I don't know, how do you want to do it? Yeah? Yeah, you could do sum. Yeah, right, so let's do sum. So I'm going to do return sum of self.coins in me. That's the way I like. And then I want to be able to do this. Well, there's one problem so far, or that it's being yelled at me, which is I can't add 20. Right, if I try and run this code, it is going to give me an error, and it's going to say unsupported operand. You can't add coin combinations in ints. How do I fix this? Anybody know? It was technically in lecture. I don't know that you've actually written code that does it yet. Yeah. Yeah, there's an add magic method. Okay. So if I want plus to exist, we do def underscore underscore add. If you don't remember this from lecture, it is the equivalent of doing like define plus. But that's just not how it's done in Python. You don't define the plus sign. You do this special syntax. Okay. How do I add a coin? Okay. Well, one way we could do this is append the coin. But this is not right. Why? Oh yeah, I like that. So if coin not invalid coins, then I should do something. No, self.valid coins because of the way I wrote my code. That's fine. What should I do? Raise. What kind of thing should I raise? Yeah, exception seems fine. I'm gonna be more specific though. I'm gonna do value error. Okay, and I'll say you tried to add coin, but must be in self.valid coins. Okay, so that's close. There's still one issue though. If I go back to my description of what it's supposed to do. Actually. This is a very subtle point. This is not a very nice thing to do to you, but I'm doing it anyway. It doesn't accept? Oh, well, actually, the add function, it's always taking the current object and adding a coin, so it's fine. This right here will actually call this function with cc and 20. Say again? Sorry. Oh, I'm not so worried about a limit. That's okay. We can keep adding more and more. Well, let's see what happens when we run this thing. Okay. Unsupported operand type for none type and int is happening on this line. Here, I'll give you a hint. If I do print cc and I run this code, it's printing none. This thing's none. Why is it none? Yeah, so we got to return something. What should we return? What type of thing should we return? It could do return self. Okay, so we're close here. Okay, so if we do this, it looks like everything's fine. Okay, we got 45. One thing that I don't like about this current approach, though, is if I do other coin combination equals cc plus, let's say 100, 1,000. If I then print out cc.value, okay, what do you think it should print out? Like, what's the right thing if the code's working correctly? Yeah? 45. But if I run the code, I'll actually get 1,045. You tried to add 1,000. Well, okay. Let's try again. All right. I added 1,000 cent coin. So I got 1,045. What? Why did this happen? Like, why did CC's value change when I did this? What do we know? What does this say about the plus operator? It has something. Yeah? It has a side effect. The side effect is that it actually modifies CC. No, don't like it. Okay. Add is not supposed to have side effects. It's a weird thing to do. You shouldn't. It's like not part of the contract of add. Why is there a side effect? Because we're appending the coin from outside to myself. Okay. While technically this works, it has a problem with being a side effect. Any questions about that before we fix it? This is a very subtle problem, but a very important problem. We want to make it immutable, yeah. And the way we make it immutable is by not having append. So we don't want to append to myself. So how do I fix it? Well, I'll give you a hint, which is we need, I don't know, a new coin combination. How do I get a new coin combination? I say, let's create a coin combination. Okay, that new coin combination should have coins in me, should be a copy of self.coins_in_me. I'm just kind of giving something away here. So I make a copy of my coins and I give it to them. And then what do I do? What's the next step? One more step here. So I made a new coin combination, make a copy of myself. I didn't quite hear you, but sorry. Oh yeah, append, right. So we're going to append the coin. Append the coin to the new coin combination. Okay. This is one way to write the code, and this should work fine. Oh, so I need to say .coins_in_me. All right. So if I run this code, oh, sorry, gotta get rid of this. So if I run this code now, CC's value is 45, and other coin combinations value will be 65. Okay. So this is an example of an unintended side effect, right? And this is a pretty challenging thing to think through. Like this, especially for an ITP student, probably feels a little heavy, but hopefully it also makes sense, even if it's a little shaky. Any questions about this? Okay. Lastly, we want to be able to print out the coin combination. When I print out CC, I get this, main coin combination object. I can't see what's in there. So what do we need to do now? Anybody know? Yeah, we need to have another magic method here that's nice. So we'll call it stir. Okay? So I want to make a nice string representation of coins. I'm just going to use strings. I'll say I'll just say coins_in_me. Do the string version of that. And hopefully that's good enough. Self.coins_in_me. So if I do that, now we get a nice string representation. That's just the lists string representation. Okay, any questions? Yeah. Why we needed to return something here? Or return some for the value? Oh, let's see. You're saying earlier we did return self here? Is that what you're talking about? That was one way to do the add function, but it wasn't right. Return self was just the first approach we did. We basically took the other coin, added it to ourself, and then returned ourself as the answer. Was the old version of add, but that wasn't the right approach. If I'm understanding your question correctly, which was, why did I return self here? And the reason we needed to give some coin combination. I don't know if I got that, but sorry if I did. Okay. Okay. So that's our coin combination class. And I'm going to get rid of iterated because I don't think it's important enough. And I want to focus on a cooler thought. All right. Okay. All right. Any other questions about this or thoughts? Yeah. So if you do this, it's a good question. If you get rid of the .copy, then we're going to run into some trouble here. In particular, when we run this code again, when we print CC's value, it's 65. Because what's going to happen is then the two different combinations are sharing the same list. Yeah. So we can think about what this equals operation does. It like binds the other new coin combination's coins_in_me variable to the same thing as my own. So it really needs to be a copy. Phone, you're too noisy. Okay. So this coin combination, I mean, this is not a sexy thing, right? It's like very workaday code. It doesn't seem to do very much. But it is nice because it prevents us from adding quarters, for example. And yeah, I don't know, just a nice little package for the next task I want to do. So I originally had an annoying exercise for you, but you're in luck. I'm not going to ask you. But I'm going to leave this here for you. If you want to do it for later, I'll post the slides. Instead, though, I want to focus on a deeper idea so that we actually have time to reflect on this while we have energy in our brains. So I'm going to talk about recursion. And I want to first reiterate. I want to state very clearly that any code in the universe that you can write using a loop, you can also write using recursion. And it is also true that anything you write using recursion, you can also write using a loop. Neither technique is more powerful than the other. I'll note that if you're using a loop, that code is often called iterative. And since recursion is so damn tricky, especially for the new programmer, you might wonder why we even bother teaching it. Well, the reason is that some programs are much more elegant if you use one approach versus the other. And in particular, the kind of things that you'll do in the data structures course next semester, there's just cases where the recursive version of the code is much cleaner. Recursive code often feels a lot like doing inductive math proofs, where you are having base cases and you're saying, okay, if the base case is true, let's prove that it's also true for the n+1 case, okay, therefore it all works. What that means is that it's much easier for some of these tricky but important, very mathy programs. It's much easier to build code that you feel is definitely correct. In the world of functional recursive programming, often it's like a brain teaser, where you're like trying to think like, how can I possibly get this code to work? But then once you have the right structure, it feels like it is correct. Whereas with iterative code, things are often much messier. So let me give you an example. On the right is the recursive implementation of the Fibonacci sequence that you may have done in the lab, where I say, hey, the Fibonacci function, if we have n as 0, we'll return 0. If n is 1, we'll return 1. Otherwise, we recur recursively fib n-1 plus fib n-2. It almost matches the math definition perfectly. If you see this code and you have written down how Fibonacci is defined, then you should feel pretty good, like it's working correctly. By contrast, this is an iterative Fibonacci implementation. It's by no means the best implementation, but it is the one that ChatGPT wrote for me, and it's pretty normal. The first two pieces look normal. They give you these two cases explicitly. And then a comma b equals 0 comma 1. If you don't know the syntax, 0 comma 1 is a tuple. And then when you do a comma b equals 0 comma 1, it unpacks this. And it says a gets 0, b gets 1. For underscore in range 2 n+1, why the underscore? Anybody know? We don't use it. It's not important. We just need to do a thing a certain number of times. We'll say a equals b equals a plus b, return b. I mean, it's also nice, but I don't think it's as nice as the recursive implementation. And there are certainly other examples, like the one we're about to do, where the iterative code is just much uglier. There are also examples where the iterative code is just way more clear. For example, finding does an item exist in a list? It's probably easier, especially for a novice programmer, to just write it with a for loop instead of doing something tricky with recursion. Or another example would be, imagine, if we go back to something we wrote earlier, imagine trying to do the extract smallest function recursively. It's a little annoying. You can, but it's just not that fun. So recursion is a really powerful technique, and it is mind-bending, and yes, it makes for good exam problems, but it is also just practically really useful in certain cases. So what we're going to do to finish up today is we're going to build a recursive algorithm for finding coin combinations. Aha, that all makes sense. That's the reason we did that. So we're going to find all the different combination of coins that we can use to make a certain amount of change. So for example, if I want to get 11 cents out of all the available European coins less than $1, then I could do a 10-cent coin and a 1-cent coin, or a 5 and a 2 and a 2 and a 2, or 5 and a 2 and a 2 and a 1 and a 1, or 5 and a 2 and a 1 and a 1 and so forth, and these are all the combinations. I want to write code that finds them all, and it just turns out that this kind of problem works really well in the world of recursion. So any questions about the goal that we want to solve? Okay. So I said earlier that one of the biggest challenges in programming is knowing the right abstractions that make your program easy to implement. That was true, for example, in sorting. Because I gave you extract smallest, then the Josh sorted method was relatively easy. You just call extract smallest once for each item. Okay? It made sorting dead simple. There are a lot of things you could do here that are just slightly wrong that would mean it would take you a lot longer. But this happened to be the right abstraction for this. With change finding, the right abstraction is quite subtle. This is pretty hard. I think you would have a tough time finding this. But here's the function that I'm going to propose as the unit of abstraction we're going to use to solve the problem. Okay? So it's a function that takes 3 parameters. Okay? And I guess I should first say, I'm going to be lazy and I'm going to set all of the answers up in a global or like a top level variable called valid combinations. That's where we're going to put everything. This is going to be a list of all the valid coin combinations, like all of these. Okay? And so the make change function is going to take 3 things. I'm going to give you several questions to sink this into your brain. It's going to take you 5, 6, 7 minutes to understand what this function even is. But then once we understand it, we're going to write it and it's going to work. Okay. So what we're going to do is make change as a current coin combination. For example, 25, 2, 1, 1. That is, I already have a 20-cent coin, a 5-cent, a 2-cent, a 1, a 1. Okay. So we have the 29, 30, 31. 31, 12, wait, no, sorry. 27, 31. 25, 27, 29 cents. There we go. I did it. Okay. So what this function does, okay, it's going to find all combination of coins that include the current coin combination. So it has to have these 5 coins, and it may have more. And the combinations that it finds need to add up to the desired amount. That's the second parameter. And then the third parameter is it's only allowed to use the list of coins that are provided. Okay? And these coins could be used any number of times. So this list will be all possible European coins or whatever market you're in. And the identified combinations are going to be added to valid combinations as a side effect. So make change does not return anything. It's just going to add to this valid combinations variable. Now already there's weird stuff here. I mean, I guess it makes sense that make change should take a combination of coins and an amount. But the fact that list of coins is provided as a parameter, as opposed to just being something up at the top level, like why is it getting passed around? That should not be obvious at all. Okay? But this is the set of abstractions that's going to make the code relatively smooth sailing, and you're just going to have to trust me that this is the right abstraction. But before we even get to using it, we have to understand what it is, because this is not easy. Okay, so one thing I always try to do in a lecture is I make it so that if you're paying attention, you cannot help but understand, and the only way I can do that is by asking you more questions. Okay, so let me give you first an example, and then I'm going to give you 3 problems to do. So let's suppose we call make change, and the current coin combination is 20, 20, and 5. Okay, so it's 45 cents so far, built this way. The amount I want is 51, and the list of coins is 5, 1. Now I did do this slide on the train, so I hope I don't have any bugs, but we'll find out. And so I believe the correct behavior of this function is that it's going to add these 2 combinations to valid combinations. Why these 2? Well, what do we note about them? Well, they both add up to 51. So 20, 25, 5, and 1. Okay, that seems good. And 20, 25, 1, 1, 1, 1, 1, 1. Okay, so both of these are 51 combinations. And what we note is we're only adding 5 and 1s, okay, to get this 51. So there's no 2s in here, for example. You're not allowed to use the 2-cent coin because it's not in the list of coins. Okay. Are there other combinations? No. Any questions about this example before I make you do some? Okay. Imagine, if you will, that the current combination of coins is 20, 10, 1, and the amount we want is 56, and the list of coins is 10 and 5. What combinations get added? I'm going to give you 2 minutes to do this problem. Feel free to talk to each other. The rest of the lecture is a waste of your time unless you understand this problem. So unless you're really stressing about assignment 3, really think about this. I'm going to use this piece of paper to do it myself. let's work it out. All right, keynote, come on. I don't want the dot anymore. Okay, well, I'll accept the dot. All right. We need how much more? That's the first question. So, oh, sorry, we have, I guess, first of all, 31. We need how much more? I think I heard someone say 25. Okay, good. Using 10, comma 5, how many ways can we make 25? 3, right. And so those ways are, overall, the thing, so what gets added? Gets added to valid combinations. What gets added is 20, 10, 1, just for my convenience, 10, 10, 5. That's the first one. So that's 2 10s and a 5. Then we'll have, okay, whatever, we're stuck with bold. Okay, 20, 10, 1. What's next? 10, 5, 5, 5. And then lastly, we have 20, 10, 1, what? 5, 5, 5, 5, 5, 5. Okay. And I ran out of room on my slide. But are we really just out? I guess we're out. No. Okay. Here. Okay. I'm doing this so if you weren't getting it, you have a moment to reflect. Okay. Oh, we're out of room again. The slides don't have to be that pretty, though. All right. Okay. I'll undo that part. Okay. I got the right number of 5s? No. One too many. Okay, any questions about this? This is critically important. Everything is this slide. The rest is going to come out of us naturally. Yeah. Right. What if the list can't form the coins? Great question. Coming soon. Okay. All right. Another one for you. Let's say we got 20, 10, 30, list of coins, yada, yada. What happens now? So let me give you guys only 73 seconds on this one. This is a mean question, and there's 2 correct answers. Okay, what do you think? I didn't give you all 73 seconds, sorry. What combinations get added? How many, I guess, get added? Okay, I've heard 0. What other choices do you have? 1, okay. I prefer the 1 approach, because it actually matches what the text says. It's the more pedantic answer that matches the comments on a slide earlier. What combination gets added if you do that approach? 20 and 10, yeah. And how many things are bolded? None. Like if you, oops, sorry. Bolded is basically like using a new coin by the standard. Before I was bolding the examples where we use new coins. So, you know, here I'll bold nothing for you. Okay, I did. Oh no, not that one. Okay, there you go. Okay. Doesn't have to be this way, no. You could actually write it the other way, but I think that the way the code will work once we get to writing code, I like it better with the 1 approach. What do we mean by that? It'll come down to base cases. Okay, so this is the trickiest one. All right, so now we'll go to, I think, a slightly less tricky one. Testing your understanding yet again. Okay. So now we have 20, 10, amount 36, list of coins, nothing. What gets added now? What do you think? Nothing, right. There's no way you can add it. Why can't I just add 20, 10 like I just did before? Like, because it doesn't add up to 36, right? So the difference here is that before, we already had hit the correct number. This time we haven't. So this one, none. Okay, and very last one. Let's say I have 20, 20, 10, 5. The amount's 36, and I have these coins. Okay, this one I'll give you a slightly longer time to look at it for a sec. Nothing again, right. So nothing. We're too big. Nothing. We already went over it. Okay. So, with all that in mind, this make change function is going to be recursive. Okay? And that recursion means I need to figure out what my base cases are. So I'd like you to try and think about for a few minutes what the base cases are. I'm going to give you, we nominally finish at 5, right, in this room? Not like at 4:50. Okay. So I'm going to give you guys 3 minutes to think about what the base cases are. Okay. So everything that I just did will give away the base cases, but I'll give you a moment to reflect. If you're writing this code, what would be the special base cases where we're done? Where we're not going to do any more recursion. So I'm just going to do it until I figure out what the base cases are on a piece of paper, and then I'll bring you back in. There's 3 base cases. That's going to be my hint. Still going to let you think about it though. Waiting 24 more seconds. Okay. All right, let's write some base cases. So if I go into recursive change, I have here nothing. All right. Okay, here's my coin combination class. I just copied it from before. Here's make change. Here we have our base cases. Okay. So I'm going to solicit some base cases from you. I'm going to write it up here so you can see the variables. What's one case where we're definitely done? Anyone? Yeah. Right. How do we know that? What do we use? If something's bigger than amount, we just return. What's that? Right? So we could do that. That's not what we do because we're using an object. We were doing like value, right? So if the value of the combination is bigger than amount, we return. Great. Okay, another example where we're done. When it's equal, right? So I'll kind of, we're going to say, so if the current coin combination, yeah, if it's equal, we're done, yeah. So if the current coin combination is equal to amount, I went Java mode on you. Hold on, get rid of these parentheses. Then what do? We return for sure, but there's something else we need to do. Add it. So we gotta say valid combinations dot append current coin combination. All right, good. There's one more base case. Yeah?
When there's no, because I assume we're gonna get like through the list of coins and there's nothing left in the list.
Right, if there's no coins, okay, it's not obvious that that's even gonna happen in the recursive call, but of course if the list of coins is 0, I'll just make this very explicit. No more, if there are no coins, then we return, okay. Now, the list of coins, like, it's not obvious that it should change anyway, right? Like, that's just something I'm hinting at. But these three base cases will be the three situations where we're done. We can think about this as fail, we went over. Success, base case, and then we have another fail. There are no coins. Okay, seems weird. Is this just a corner case? I don't know. Okay, now let's try and write the recursive part. So if I have neither succeeded nor failed, then I'm going to continue the search. Okay, so this is really cool, but challenging. And in another universe, I don't know. And I would make you guys sit down and think about this for a half hour and argue with each other and find the answer. But I'm going to kind of spoil it a little for you. So one way to continue the search is what? Anybody have any ideas? Preferably, maybe some small fraction of you have seen this problem before, and if so, don't answer. So we want to keep looking. Okay. We don't want to do the exact same search again. We need to tweak it in some way. Yeah? Right, so use the first coin is one way to do it, okay? So the way we could do that is current coin combination plus list of coins 0, okay? So we're going to say, let's keep looking. We're going to use that first coin, which will be, I don't know, I'm going to flip them around, 50, 20, 10, 5, 2, 1. So let's try it using the 50 and see what happens, okay? Amount, do we need to change the amount we're looking for? No, same amount. List of coins, do we change the list of coins? No. Okay. So that is, let's try using the first coin. Okay. Now, that is a great search. Now, the part that is not obvious is that's not the only thing we need to do. Okay. So we could try using the first coin. We could use the 50-cent piece. What's the other thing we could do? Yeah? Nope, not the smallest. I'm gonna, like, one possibility is to use the 50-cent piece. What's the other choice? Use something else to yeah, there's a simpler answer though. You could use the 50-cent piece, or you could logic, yeah. For example, 10, 5. 10. Well, you could use something instead of the 50, but let me say why I don't like that answer. Let's say we're at 35, we need 50. Like, one choice is we need, let's say, 55. We could use the 50-cent piece, but the alternative is not using some combination that is the 50-cent piece. How about this? Let's try using the first coin. The other possibility, don't use the first coin, right? So you can use the first coin or you can not use the first coin. Do you agree with me those are the only two logical possibilities? Yeah. Right. Yeah. Exactly. So we'll do list ignoring top coin equals list of coins dot copy, and then we do pop 0, and then we pass that, and then we're just saying we're not, like, same coin combination, but we're only going to use the non-top coins. Okay. So this is use the first coin. This is don't use the first coin. Okay? I claim that this is, assuming I didn't mess something up, just correct, and it gives you the answer. Okay, so for example, I might have messed something up though. Change 61, print valid combinations. Okay. It has to work because that feels good. Okay, hold on a sec. Okay, so we didn't get all the combinations. 61, 50, 20, 20. That's not even correct. Am I running the wrong file? Yes. Okay. All right, here we go. So what I just got here, these are all the ways of making 61 coins, assuming I wrote it correctly. 50, 10, and 1, 55, 5, and 1, 55, 2, 2, 2, and so forth. And, you can count them, but I feel pretty good that it's correct. Let's try 11. 11 we can actually double check. Okay, 10, 1, 5, yeah, that's what we had on the earlier slide. So to me, when I first saw this kind of programming, it felt almost like a nightmare. It's too clean. It feels like it didn't actually do the problem at any point, right? Like I just said, I had a series of kind of, especially in the middle of a lecture, where you're not really digesting everything because you're just being dragged by a train of my words. But it was like, okay, what do we do? Well, we had these 3 base cases. You're probably not fully convinced that those are the only base cases, but they are. And then this idea that these are the 2 possibilities also probably feels a little shaky. And so to really, really feel good about this, you have to do it yourself. Just watching me do it is only going to be partially satisfying. But the idea, basically, the intuition, was we could use the top coin, which was let's make change using the top coin, or let's make change but ignoring the top coin. Those are my 2 possibilities. And just this right here gets us the answer. And this is much cleaner than any iterative solution that I can imagine. So I think that's pretty cool. Okay. So I have one more thought today. So I will say that I want you to feel the intuition for that, but not to feel like you definitely got it, because it's pretty hard, okay? All right. So in the email I sent out, where I was pitching today's lecture, I said I was going to talk about some problems, and I was going to talk about foundations of computer science. So I said we were going to do depth first search on a tree. Did I do that today? What do you think? I claim yes. In fact, I think that I think we did a depth first search. So what the heck is this tree? What was the tree?
A tree is essentially a graph without...
It's a graph without cycles, sure, yeah. But what specific tree did we search? Yeah? The coin combinations, right. Was the tree rooted as defined in that class?
What was that?
Is the tree rooted? Does it have a root?
Yes, sir.
Yeah, what's the root?
The coin combination.
Yeah, the coin combination of what? What's the root of the tree? Which combination of coins? No coins, just the empty coin set. Was it a binary tree? No. How many leaves? How many children did the nodes have? As many as there are coins. So each node had its own child, which was the 50 child, the 20 child, and so forth. So it was a hexary tree. And the search we just did was a depth first search. So this was depth first search. And that's why we ended up with this kind of structure, where we found all the 10 combinations first, then all the 5 combinations, then all the 2 combinations, is that we did a depth first search. We didn't really think about it as an explicit graph object, and yet we did. Okay, so wrapping up. What do we do today? Well, you looked at functions as arguments, functions as return values, object orientation and immutability. Coin combinations couldn't change, and recursion. Now, I hope that this felt good, it felt reflective, but that you also still felt like there's some interesting challenges here. If there's something you wanted to get out of this lecture that you didn't get out of it yet, I'm going to post everything, and what I'd recommend is that you try and actually do the recursive change problem from having no comments, maybe in a week or so, just to reflect on it. Anyway, that's all I got for you. So I'll see you one more time in 2 weeks. So Zhao Chun's doing one more lecture, then me again, and that's it. Good luck on assignment 3. Sorry that I haven't done it myself, and I have to go quite soon, but I can stick around for a few minutes for questions. Thank you, everybody, and I'll see you in 2 weeks. Thank you.